So coming back to area sums, we want to use this summation notation to find actual values of these a underscore n and a bar n, like we have here. So we start out with having f being a continuous, non-negative, and increasing function defined on some interval from a to b. So in this case, we have this function, right? It's clearly continuous, it's clearly non-negative, at least on this interval, and it's increasing, right? Later on, we will see that we can relax some of these assumptions, but to begin with, let's keep it simple. Then we take this interval from a to b, and we subdivide it into n intervals of equal length. So if we have an interval from a to b, the length of this will be b minus a, right? So the length of each subinterval should then be b minus a divided by n. So let's call this length of each of the subintervals delta x. So this is the increment in x values. And then we put xi equal to a plus I delta x. Why do we do that? We do that because then we can say that a naught or a 0 is just a, right? X naught is just a, because a plus 0 times this number is of course just a. But what is x1 then? x1 is a plus this interval length. x2 is this number, x3 is this number, and x4 is this number, in this case where n equals 4, like we have here. So always you will see that xn will be equal to b, because you have n times this number will just be b minus a. B minus a plus a is of course just b. So in this fashion you get that these numbers now indicate the start and end of each of the subintervals. Now since this function is increasing, we know that an underestimate for the area under this graph from a to b is the sum of the rectangles whose values are exactly the lowest value of the function in this subinterval and in this subinterval and so on. And since the function is increasing, the lowest value will be at the leftmost endpoint, right? So an underestimate like this will be something we can write like sum from I equals 1 to n f of xi minus 1. So this is our way of writing the leftmost endpoint of the subinterval times the length of the interval. So putting in 1 will tell us that this is f of a times the length. So this will be the area of the first rectangle. Then we plug in 2, then it's the function value here times the length of the interval. So we get this area here, and so on. And an overestimate will in the same fashion be something we can write like this, where the only difference is that now the height of the rectangle that we are taking the area of is the rightmost endpoint of the subinterval. And why is that? It's still because it's an increasing function, so the maximal value will be at the rightmost endpoint. So this is a way of writing an overestimate. Now, the point here is that if you look at the difference between the underestimate and the overestimate in reverse order, because we know that the overestimate is the largest number, right? This is something we can write like this. This may be a bit surprising that it's so simple, but let's see why. So basically, you can see it on this drawing here. You can see that there's a rectangle down here. Then there's a rectangle up here. And there's a rectangle over here. Clearly, this rectangle, having this line as the roof has the same areas as this rectangle with this line as the roof, right? So these two rectangles cancel. The same applies for this rectangle and this rectangle down here, and this rectangle and this rectangle. So in the end, the only rectangles that we need to look at the difference between is this one and this one. Right. Everything else cancels. And the way of looking at it is to say that, well, the difference here is this area, the difference here is this area, the difference here is this area, and the difference here is this area. And what is the length here? Well, it's delta x. What is the difference, the total difference in height? Well, this was f of a, and this was f of b. So the height of this triangle over here, rectangle over here, is f of b minus f of a. In any case, no matter how you come to the conclusion, you will see that you get this number b minus a divided by n times f of b minus f of a. And clearly, b and a are just constants. F of b minus f of a is just a constant. And what happens when n grows? Well, this constant number will be divided by something that grows bigger and bigger and bigger, right? So in the end, you will see that this product tends to 0 as n tends to infinity. And since the a underscore n are underestimates and the a bar n's are overestimates, you have this series of inequalities here, which tells us that since these two numbers approach each other, we will also get that the actual area of these underestimates and the overestimates will tend to the actual area. So let's see what happens if we increase the number of subintervals. You can see that you get more and more rectangles here, right? And the difference in height between these rectangles you see up over here looks like this. Clearly, the total area of this tends to 0, right? We just have to increase the number of subintervals sufficiently to get this area to be as small as we want.